What if your VPN isn't actually the problem? Because whenever connections slow down, drop, or randomly disconnect, people blame the VPN first. But the real culprit isn't often sitting between you and the VPN server, your internet service provider. And sometimes it's not bad infrastructure or weak signal, it's international interference. Which means the real question isn't, why is my VPN failing? It's, who is interfering with the connection? And what one engineer recently uncovered completely changes how you look at VPN issues forever. Virtual private networks or VPN are supposed to do one thing: create a secure private tunnel between you and the internet. But over the last few years, users have reported a pattern: VPN randomly disconnecting, sudden drops in speed, certain servers refusing to connect, and streaming services breaking only when VPN is active. And here is what makes it confusing. Everything else seems normal. Your Wi-Fi works, your apps load, your internet feels fine. But the VPN struggles. This is where most users assume it's my VPN provider. But engineers analyzing network traffic are seeing something else entirely. The problem isn't always inside the VPN. It's what happens before the VPN traffic even reaches its destination. And that's where ISPs comes in. Because your ISP is the gatekeeper of every packet leaving your device, and that control changes everything. Let's simplify what's actually happening. There are 3 layers in every VPN connection. The first layer, your device. This is where the VPN starts. You hit connect. Layer 2, your ISP network. This is the middle layer, the road system your data travels through. The third layer, VPN server, the destination that encrypts and routes your traffic. Here is the key insight. Even though a VPN encrypts your data, it cannot hide the fact that you are using a VPN. Your ISP can still see you are connecting to a VPN server, how much data you're sending, and when traffic spikes occur. And in some networks, that's enough. So what's actually happening? Subpoint 1, traffic throttling. Some ISPs reduce speed for VPN traffic because it consumes higher bandwidth and is harder to optimize, resulting to slower connections, lag spikes, and unstable tunnels. Subpoint 2, deep packet inspection. Advanced ISP systems can analyze traffic patterns, not content, but structure. They detect VPN protocols, including OpenVPN, WireGuard and IPsec, and encrypted handshake behavior, resulting to blocking or interference. Enforced reconnections. Subpoint 3, routing inefficiency. Sometimes ISPs don't block anything, they just route VPN traffic poorly, resulting to high latency, packet loss, and random disconnect. So the VPN isn't failing, it's being reshaped by the network it runs through. Now let's go deeper into what engineers are actually seeing in the real-world systems. Case 1. Corporate VPN instability. Large companies using VPNs for remote work often report teams disconnecting during peak hours and video calls dropping when VPN is active. What engineers found. The ISP was not prioritizing encrypted traffic during congestion. In part, remote employees experience instability, not due to corporate systems, but ISPs level traffic shaping. Case 2. Streaming plus VPN conflicts. Users trying to access geo-restricted content says VPN works for 10 minutes and then streaming fails or buffers endlessly. What's happening? Streaming platforms detect VPN's IP ranges, but ISPs sometimes add extra latency to those routes, making them unstable. In part, every working VPNs become unusable under load. Case 3. Gaming latency spikes. Gamers using VPN for privacy or region switching report sudden ping drops, rubber banding, and server disconnect. Engineers traced it to ISP routing VPN traffic through congested international nodes instead of local optimized paths. In part, your VPN is technically connected, but practically unusable. What changes in job roles? This is where things shift. Network engineers are no longer just configuring routers and maintaining uptime. They are now analyzing ISP behavior patterns, dictating traffic manipulation, and optimizing encrypted routing paths. And a new skill set is emerging: VPN tunnel diagnostics, DPI evasion techniques, and hybrid routing architecture design. Networking is becoming less about hardware and more about behavior analysis. As network becomes more automated, there's a common misunderstanding that traffic systems are making independent decisions in isolation. But in reality, most of what happens sits inside ISP-controlled network infrastructure, especially during peak hour congestion in backbone and peering routes. These systems are designed to optimize traffic flow, manage load balancing, and stabilize network performance under heavy demand. But they don't understand real-world context, like whether traffic belongs to a remote work VPN section, whether a connection is supporting critical business infrastructure, or whether encrypted traffic is time-sensitive or casual usage. So what looks like simple bandwidth optimization on the surface can directly affect VPN tunnel stability and performance in practice. In enterprise ISP environments, engineers often observe this kind of behavior in routing logs and packet-level diagnostics, where encrypted flows behave differently depending on congestion conditions and path selection logic. This is where human interpretation still matters, because when encrypted traffic behaves unpredictably, someone has to evaluate what that behavior actually means inside the system, not just in terms of throughput, but in terms of impact. That is why networking roles are shifting from simply maintaining infrastructure to governing how large-scale routing and traffic systems behave under real-world load conditions. And that's exactly why VPN performance can vary depending on how ISP systems interpret encrypted traffic flows in real time across different network paths. next phase of networking isn't just faster infrastructure, it's deeper interpretation of traffic behavior across the entire network stack. We are moving towards systems that operate in real time across multiple layers of decision making. Real-time encrypted traffic classification, where network analyze encrypted flows based on behavior patterns by timing, packet structure, and section dynamics rather than content. Dynamic routing based on congestion scoring, where ISP backbone systems continuously adjust path selection across peering and transit nodes depending on live network load, latency, and stability metrics. Adaptive VPN tunnel behavior, where VPN connections can automatically switch protocols or adjust routing paths when they detect congestion, packet loss, or instability in underlying ISP networks. But what this means for users is important. VPN issues that feel random today may become harder to diagnose in the future, not easier. Because instead of clear failures or disconnects, you will experience subtle, continuous adjustment happening inside routing layers and congestion systems. Performance won't always break visibly. It will shift dynamically in the background, and that changes how we interpret network problems entirely. They won't disappear. They will just become embedded inside the behavior of the network itself. So the next time your VPN slows down or disconnects, don't just ask, is my VPN broken? Ask something deeper. What part of the network is shaping my connection before it even reaches the VPN? Because in most cases, the real issue isn't your VPN at all. It's the invisible layer controlling how your internet is allowed to behave. If you found this breakdown useful, subscribe for more real-world technical breakdowns where we pull back the hidden layers of the internet and uncover how your data actually moves behind the scene. Add a comment below. Have you ever experienced VPN issues that didn't make sense?